So hi, thanks everyone for coming. And this is my talk is about dynamic time warping, which is I'm going to talk about aligning market data, which I think is a big problem that a lot of us have faced if we're in capital markets, trying to look at market data and trying to figure out what's going on. So a little bit about me. I basically fell down the Q rabbit hole 2017, and then ever since then I've been doing array-oriented programming and finding basically the similarities between computer science problems. So it's a lot of curing theory, like optimization and performance optimization. So that's portfolio management. And if you think about it, basically everything is the same problem, which is stuff goes in the box, stuff comes out of the box. And the question is, what do you do inside the box to make things not fall apart? And that's kind of been what I've been working on for, I don't know, the last 14 years. And disclaimer, the views in this presentation are my own and do not represent the opinions or positions of my employer. So none of this is backed by jump trading, but anyway, this comes from my experience. So what I want to talk about. Basically, market data is really messy. So. And there's a lot of problems with them. First of all, inconsistent timestamps. You get market data from different sources. The timestamps aren't necessarily aligned. Just because an event happens in one data center at time t and another data center at time t+1 doesn't mean that the event happened in the first center, before the second data center. There's clock drift. There's network latency. There's just a lot of reasons why timestamps are not exactly what you want them to be. The second thing is market data tends to be very, very non-stationary. There's no easy pattern to detect. If there were, that people would be making money, making sure that that wasn't the case. So market data just generally tends to be very dynamic, and what that means is there's no really easy way to just interpolate or align things just by saying oh, I see a trend, let me put this trend on top of that other trend. It just has a lot of, it's kind of just very noisy. The third problem is there might be implementation differences. Some of them are deliberate. Some of them are accidental bugs introduced by various vendors. Exchanges have different conventions. Exchanges might offer the same feed in hardware and in software. They might offer the feeds in the hardware might be different than the feeds in software for performance reasons, for legacy reasons, for all sorts of reasons. So there just might be differences for the same, essentially the same data, but it might just have different cases. And in the best case scenario is you're dealing with you're dealing with Apple, and there's 17 U.S. equity exchanges. Essentially it's exactly the same Apple security. You're buying Apple. It doesn't matter which exchange you buy it from. It's always the same Apple, but you still have 16 or 17 different exchanges, and every exchange is sending you their book feed, their level feed, and so there's just naturally going to be they're going to be the same data, so same time series of NVBO data, but it won't necessarily be aligned in any there's no sense in which it's exactly the case that there's no way to talk about what is the linear sequence of Apple's prices. They're happening simultaneously, and depending where you're viewing it from, you will see one event happen before the other. So if you're at one data center or another data center, you will experience the price of apples happening in different, essentially different series of Apple prices. And then there's sort of the natural fragmentation. So that's the best case. The second case is you actually are dealing with you're actually dealing with something that's similar but not the same. And then there's just fragmentation, sort of just because, for example, in Japan you might be trading you might be trading Toyota, and then in the US you're trading Toyota. The Toyota in US is an ADR, so it's effectively it represents Toyota, but it's not during the same market hours, and so you'll just have, they're not exactly the same security. So at that point, again, you have natural fragmentation, and so the market data sources are different, and you want to try to find something to kind of say, when I saw this sequence of events, I saw this same exact sequence of events at this other place, and they match this in this way, and so I can make a statement like, oh, if I bought here and sold there, then I would have made money, or I didn't, and so such like that. So that's kind of why market data is just kind of hard to deal with. And then why alignment matters. So I want to just a little bit step back and say there's a lot of reasons to align market data. The particular thing that I had to do was try to understand. I had one feed, and the feed was already like, we thought this was like the golden source, and we were making another source that was going to be faster, that was going to be supposedly going to be an improvement on the first source. And the first thing you want to know is, did I even like hit the target? Did I get to the golden source? So I want to find cases where my news feed is giving me something that my old feed wasn't, and I want to make sure that that is all an improvement. It's not just like a bug or something, or I'm just finding an anomaly in a data set or something like that. So I have, you might also be trying to figure out, like, I'm building this new data source, is it actually faster? I thought it was going to be faster, but actually I introduced some weird dependency, and now it's actually slower than the old data source. So there's a lot of I need to make sure that these two time series are the same, and that my new source is actually better than my old source. And the third reason you might want to align data sources is you might actually have a trading strategy that's baked on the fact that I can actually trade these two things at the same time or near the same time. And again, so you want to say, oh, when I saw this asset move, I also saw these other assets move, and I expect this to happen. And so this is like these two things are happening essentially simultaneously, and so I can actually trade based on the fact that they're happening, that I expect something to happen. So that's sort of there's just a lot of reasons why you might want to align market data, and there's a lot of reasons why it's actually quite hard to do it. And so traditional methods might be just struggle with all these difficulties. So first of all, the time series, again, because of the fact that one data center is maybe in a different place, or because there's just jitter, or there's random hiccups, there's not like an easy way to say oh, this one always precedes this other data center by exactly this fixed amount, so I can just do a shift. Sometimes that happens, and that's easy, but usually there's a lot of noise in how to align the two or n market data feeds. And the other reason that it might be difficult is you just have basically your data is very noisy. So you might see a spike. So for example, in market data, you'll often see, depending on where you're sitting, you might see the book narrow and then uncross. So you might, for example, depending if you saw the bid, you might see the bid. So when I say bid and offer, I'm thinking about a book, the best bid and the best offer. They're relative to each other. The offer above the bid, but I might see someone try to narrow the gap, or I might see someone step back. And depending on where I'm sitting, my view might be the spread widened and then narrowed, or it might have narrowed and then widened. And so there's these effectively you get these spikes in what the best bid and offer is. And so again, any kind of real world analysis where you're combining data sets, you're going to have this problem where trying to line them up is rather tricky. So I borrowed a solution from, this is an old algorithm from 1960s called dynamic time warping. Sounds fancy. And what it basically does is it lets you find a best approximation to take one series and transform it into the other series. And it has only a few requirements. So it basically it creates a distance between two time series. And don't worry if that doesn't make sense yet. I'm going to explain it a little bit more. Basically, I'm going to try to figure out what is the way, what's the optimal way to transform one time series into the other. And so it was developed for speech recognition in the 1960s and 70s, and basically it was used to say, oh, I'm listening, I have some audio, and I want to understand what the people are saying, and so people speak at different paces, and I have some canonical recording of people's voices and what they're saying, and so I'm going to try to transform one person's speech into another person's speech. That's my canonical, and that's how I'm going to measure, to recognize what they actually are saying. And these are some sources. So this is sort of the most canonical slide. This is the slide on Wikipedia for this image of transforming these two series. You'll see the top one and the bottom one. The top one is one of the time series. It's a graph that has a few spikes. And then the second one looks like a similar time series, but it's a little bit different. And those dashed lines are telling you how to align the data points so that the peaks are the same and the troughs are in the same places. And that's kind of the idea is like I'm going to show you how to like convert one time series into the other one. So we're going to have a few assumptions that we're going to have to make, though, to do this alignment. The first assumption is no data gets to be skipped. All the data from both time series are going to be considered. We're not going to just arbitrarily throw out data points because, again, we don't know in advance like what data is garbage and what data is not. So we're just going to make an assumption that all the data that we get is good, and we're going to just even if it's garbage, we're going to align it. If that's still good, it's going to be okay because at the end we're still going to find the best path. So since we're finding the best path, any garbage data points will have affected all of the paths that were under consideration. And the way we're going to make sure that no data gets skipped is we're going to start from the first point on the first sequence and the first point of the second sequence, and we're going to line those two up. And then so I want to just kind of make sure that the last sequence index of the last sequence is going to the last index of the first sequence and the last index of the second sequence are also going to be aligned. So we're going to like kind of clamp down the ends to tie those together. And then we're going to try to figure out at what pace we're moving each time series. So, but no data point, just because no data point is skipped doesn't mean that it's the only match. It's not a one-to-one mapping. So if one of the data points has like 10 points and the other one has 100, where you can still do an alignment, some of the data points will be mapped more than once. And the second key assumption is that we can never go backwards in time. So basically, as we progress in one time series, we're going to also progress in the other time series, or we're going to stop, but we're never going to go backwards. So we're never going to reconsider and like shuffle the data. And that's kind of what makes this a time warping problem, not like a time shuffle problem. It's just we're going to slow down or speed up time, but we're never going to shuffle time around. And so this is just an illustration of how we're going to do this alignment. So you can see that as we progress from the blue series to the green series, we're always moving forward in time, and we're always finding a point that we're going to line up to the next point. And so what this just kind of gives you an illustration of is what does it mean to transform the blue into the green line or the green line into the blue line? This is going to like tie every point from the blue line to the green line, and we just kind of keep forward. As we go forward, we're just mapping forward in time to the next point, and then as we get there, we'll just consider only the future points that we need to go on to. So a little bit of like code. I'm going to try to, depending on the level of of the audience, we can go back for questions and go through it in more detail. But this is the Wikipedia code, like the code on Wikipedia for doing this problem. And effectively, we have something called like the distance, which is just like the cost from going from a point X to a point Y, which is one series and the other, and we just take the absolute value of the distance, just like the difference between the two X and Y values. And then we're going to build up this whole array, and then we're going to minimize it. And you can see there's a lot of code, but really boils down to the following 4 steps. Compute something called like C, this cost matrix, which is just for every series, let's say we call it, we have 2 time series, X and Y, and for the I is going to be, the ith entry in the X series, and J is the jth entry in the Y series. We're going to compute essentially a point-by-point distance, which is just going to be this just X minus Y, and then take the absolute value. Then we're going to go and initialize this DTW matrix, which is just going to be currently infinity. Like it's going to say everything's infinity. We don't have a good path. Then we're going to set up some boundary conditions. So we're going to say that the first point has to align, which is basically just saying the first entry of the DTW matrix is exactly equal to C. It should be C0, C0. So DTW 0, 0 is C0, C0. So that's just the matrix essentially of just that first entry, that first diagonal entry into that matrix. And then we're going to just initialize the first row to be the cumulative sum of the first cost matrix. And then from then on in, it's this recursive formula of like, we're always taking the min of the 3 neighbors. Okay, so you have this code, it exists, but like, and there's many packages already that exist. Why like bother translating this into Q? Why why am I talking about this? Well, sometimes you look around and you're like, oh, we have a wheel, but it feels a little square, and so maybe you should like round it up. So, and you also get additional insight by implementing it. Once you implement it, there's other ideas, other kind of considerations that come along. There's adaptations. There's new applications that come together. So, and a lot of reason is just like the data might already be in Q and it might be faster, and it's a good time. So, and then sometimes people keep asking you, why are we reinventing the wheel? And just send them this cartoon. Oh, sorry, I'll go back for a second. So people say like, oh, don't have external dependencies. One of the other reasons to translate to Q is you don't have to reach for another library and then that library breaks on you. You can just have the code right there in front of you and you can just fix it if necessary. So now I'm going to just go back over the same 4 steps, but now in Q. Compute the cost matrix. So we're going to factor out this distance function and just compute it directly. And that looks like this: the absolute value of x minus each y. And for those familiar with like multiplication tables, this is just a multiplication table, but instead of a multiplication table, you have a subtraction table. So it's just x minus each y. So if that like rings a bell, that's what this is doing. And then next, we're going to create an accumulated cost matrix. Well, we don't have to do this because, like, why do we do that? And then 3, we have boundary conditions. Okay, so we knew that the first row is just equal to the cumulative sum of that cost matrix. So there's that. It's done. So that's the cumulative sum. The first entry in the DTW is just the cumulative sum of the cost matrix. And then the last step is this recursive formula that says we're going to find the minimum of the 3 things so far, and of the neighboring cells, and take the minimum of that plus the current entry, and that looks like this, which I grant is a little confusing. But if you bear with me for a second, essentially x is the current cost. So you'll see x is the current cost that we had in that DTW matrix. Y is the cost to edit at the particular point, and then A is the accumulated cost as we go, and then C is the cost of the row. So basically, what we're going to do is keep scanning from left to right, and just take the minimum of the current cost, and then just go along and keep adding that to the current cost. And again, don't expect anyone to get this on the first read, but that's if you just label this, if you kind of put this in a box for now and put it in a box and just say this is the min cost so far, then you can say the min cost so far over the scan of C is the DTW function. And so putting this all together and getting rid of all of like the extra variables that we didn't need, you can fit it nicely on like one line. So this is which is always like very satisfying for some people. Now, if we want to find the optimal warp path, which is the sort of like we have the cost, but now we want to figure out how to actually map these 2 data points together. You have this matrix, and what you do is just walk from the bottom right-hand corner back to the left to the top left. And I will show you an illustration. I think this will make things a lot more clearer. So this is computing the cost matrix, and you can see what's going on is we have this matrix. It starts off all dark blue, which is essentially everything being initialized to infinity. And then what we're doing is computing those 3 yellow highlighted cells and picking the minimum of those 3 plus the current cell and making that the new value of that cell in the middle, the red cell, the bottom right-hand cell. And we just keep walking down the matrix, and that's all that is happening in DTW, which is dynamic time warping. All that's happening is just going down the rows 3 cells at a time and computing the minimum and adding it to the current value. And when all that entire matrix is filled in, we do this, and we go back and greedily find the best path. And the best path, we start from the bottom right-hand corner and just look at those 3 next neighboring cells to pick which is the minimum, and then we just go along that all the way back to the top left. And that's the path that transitions the X series into the Y series, where the Or you can think of it as the x's along the columns and y's along the rows. So now you go back, okay, fine, but like, why are you re-implementing this in Q? Like, this is very cool, but okay, like, what did you actually gain? One is this is way more, like at least 10x faster than a few of the Python packages that I'll implement it. Two, we can add a bunch of extensions. So as an example, in market data, you might have a different cost. When you're dealing with sensor data, you have noise, but when you have market data, the actual precision of the bid and offer, you don't expect there to be any noise in that. You actually expect exactly the market data to come in as it was printed on the exchange. Like, you don't expect, like, if one of the exchanges says the price was 10 by 11, you don't think that the 10 is like a little noisy. You just think it's exactly 10 and exactly 11. So you might change from absolute distance of x minus y to something that looks like x not equal to y. So if x is not equal to y, then that is a difference, and I don't want those two things to align. And I don't care about the actual like relative difference. I just care about like, are they exactly matching? You might want to line up the bid and ask simultaneously. So you might think that like my bid and offers are coming in at the same time. So what I want to do is I want to line those up, so find the best match so that the bid and offer from both of my market data feeds are lining up along the best alignment. And again, all you do there is you just transform your cost function to something else, one that takes in the bid and offer at the same time. And this is called graphical DTW, which sounds very fancy, or multidimensional DTW, which is more explicit, but it's doing exactly the same thing. And that's just the sum of the absolute value of x minus y. So that is exactly what that cost function looks like. There's more extensions that are available to us. Locality constraint. So this sounds also, again, pretty fancy, but all it's saying is I don't want to go down a path where I'm aligning the first point of one series with all the points of the other series. I want to make sure that like I'm always progressing in time about equally in both series. And so what that looks like is create a matrix that has zeros in the middle, in the diagonal, and infinities on the edges. And I will give you a quick, this is the code to generate this locality matrix. It basically just says like if I'm shifted too far to the right or too far to the left, then those will be infinities. And what that looks like is this. And you can see there's zeros in the middle and infinities on the edges. And what that basically says is that when I take the cost matrix, I will never go too far into the edges. And so when I find the best paths, those wings of the matrix will kind of be excluded from my search, which means that I'm always going to be progressing in time somewhat evenly through the series. And then this is, once you kind of get rid of those wings, you can actually have more efficient implementations, and I will not bother going through them here. Of course, if there are questions, I'm happy to explain it in detail. So what I wanted to kind of show is just like in practice example from like a synthetic data to just kind of explain how this can be used in practice, or like how I use this in my work. So generate 4 sets of market data that exist on 4 different exchanges. We have a bid and offer for every exchange. The series look essentially the same. There's some jitter from every exchange. They look a little bit different. There's a little bit of noise, but they're basically all the same. Then construct 2 different best bid and best offer feeds. So we'll just look, and for one of the feeds we'll say there's a fixed amount of latency, which is just like how long does it take from exchange A to my place where I'm consolidating, creating the book feed? How long does it take to get from exchange B to my book feed? That's a fixed amount. And then add something called like jitter, which is just like sometimes random things happen, like market data comes in really bursty, a lot of people, and like I have random delays, the network gets clogged, whatever it is, there's random reasons why things get delayed. And model that as an exponential. So mixed exponential is a little bit slightly fancier, but basically instead of just like it always arrives with some probability, like what actually happens is you flip a coin, and 1 out of 100 times when you get a heads, what'll happen is I take the exponential from some very large spike, which is very common in market data. You'll see this basically the market data comes in really, really fast, and then occasionally there's a hiccup, and you get an unexpected few millisecond delay. And now you can take these 2 series and plot them on top of each other with the new align series. And what you can then look at is, if you see the aligned series looks basically, there's like no point where the blue or the red show up above through it, but there are these little purple points where the yellow series is not quite covering up the points, and those are all the anomalies. So this is a way, essentially in real time, to line up two market data feeds, and then you can ask questions about those purple points, about those essentially they're anomalies. Those are like cases that are points of interest, and those are either tradable events, or they might be bugs, or they might be latency spikes, or they might be like there's a lot of things that you can kind of drill into to understand like what's going on at that point. Wherever the things perfectly align and there's like there's perfect overlap, you don't have to worry about those cases. In fact, those might be cases where like some kind of like pair strategy might work, where you just think that like things are effectively the same, so you can actually just trade them normally. But all of the little kind of like outlier cases, they'll like just immediately pop out in the series. And I want to talk about. There's AI's on the mind, and so one of the things that you can do that's kind of interesting here with this new tool, like you have a new hammer, so everything looks like a nail, is you can instead of correlation, you can just look at that last entry in the matrix. So when you're computing two similarities between two lines, what you might want to do is just, instead of using correlation, which only applies if the two time series are exactly the same length, you can actually do a dynamic time warping distance between two time series that are of different lengths. So you might have a daily series and a weekly series, or a daily series and some 5-minute series, and you can now go and compute an actual similarity between these two time series and then make some predictions based on that. You can do, again, like anomaly detection. You can say, so again, you create these points of interest, and now you can highlight those to your model, and that essentially annotate the time series for some other, for further down, for feature selection. And you can also do regime detection. This is like, you can create essentially like, what are like idealized regimes of the markets. Like you believe the market is in sort of like a momentum swing or a mean reverting swing, and you create these idealized time series. You then normalize any new time series you get, and then you say, is it more similar to the momentum period? Is it more similar to the mean reverting period? And you'll always get an answer of like which one it's more similar to, and then from there you can use that as a feature in your AI model.